In this video, we're going to take a field trip to the center of the Earth. Well, okay, maybe not the center and maybe not actually a field trip, but we are going to go on an amazing journey of discovery in this video, of peering at what lies underneath the crust and down into the mantle. As we've been going through these series of videos, I've been sharing this knowledge schema with you to keep our organised learning and understanding nice and clear. And we've noticed that there's been an expanding evidence base, which has led to this evolving theory. The evidence that we first looked at was Wegener and his continental drift evidence, the evidence from the continent, and Arthur Holmes' initial hypothesis of convection currents perhaps driving that, which led then, following the Second World War, to a plethora of seafloor evidence coming to light, and Harry Hess and his idea of seafloor spreading, and again he resurrected the convection currents, both of which saw the plates being moved passively by convection currents in the mantle. But what we discovered in the last video is that already in the late 60s to early 1970s, as plate tectonics a theory began to emerge, that even by that stage, this model of convection currents driving the plates was being rejected. And the key points moving forward: convection includes the plates and indeed is mostly driven by the plates. But we did leave this story in the early 1970s, and there have been 50 years since then, and the theory has evolved. So what we're going to do is to go and explore some of that evidence that's come to light since the coalescence and emergence of the theory of plate tectonics. And we're going to explore how that has helped us to understand better the mechanisms operating in the mantle, most notably ridge push and slab pull. And it was this model that we came up with last time, that what is the main driver of plate tectonics, it seems, is the sinking of cold, old, dense lithospheres. This is cooling from above and convection sinking due to the negative buoyancy of the plate and the slab as it sinks down. That will pull the plates, creating this sense of tension here, which thins the plates, allowing some of the mantle material, which is solid but will flow, to rise up well passively in response to what's happening at the plate margin. Because it brings the hotter material closer to the surface, that brings the heat up and gives it a positive buoyancy. And indeed, the new crustal material that is formed by the magma that is formed by decompression melting is young and hot as well. So all of that really contributes to that positive buoyancy, allowing the ridge to rise up, and then the older material will slide down the side of the ridge as new material comes up to replace it, and that pushes the plates apart. So the main drivers are slab pull and ridge push. You do have convection in the mantle, but that convection is largely passively induced by the moving plates. The plates are the active component of that top-down convection. Just to note, in terms of fullness of explanation, there is heating from below and upwelling of these mantle plumes. Unlike the slabs which come down as sheets, this comes up as a single conduit, maybe a couple of 100 kilometers wide, which can bring hot material to the surface to produce hotspot volcanism, such as at Hawaii. There is some early indication that these two might interact in some way. Some of the material from the slab graveyard might get melted and brought in here, because of the geochemical signatures we're getting at the surface seems to indicate and hint that that is the case, but we're still very much in the early days of understanding how they interact. So mantle dynamics, your top-down cooling of slab pull and ridge push, that's what pushes the plates and pulls the plates, and then you've got your bottom-up heating of these mantle plumes that are not related in most cases to the plate margins. That is our model, right? It is a model. It's certainly a simplification of what goes on. It's certainly not the last word. This will evolve, but this represents the consensus of our best understanding at this stage. Again, we'll just touch base quickly with the notion of powerful knowledge. That's what's been guiding us as we go through here. The ability to get access to this knowledge, which is created by specialist communities in accordance with the rigorous demanding and processes. It's reliable and it's truthful. It's the best that it can be. But particularly here, we're going to be looking today at what this enables. It's not as powerful if it enables you to envisage alternatives. It's powerful if it enables you to question it and the authority in which it's going to be based, because we're going to be using some of this knowledge today as we go on our field trip. But as well as powerful knowledge for our pupils, I'm hoping actually that you're having something of an experience of that as well. Right back at the first video, I showed you this top diagram as one of the slightly more complex versions of the mantle dynamics that we uncovered in our Google image search. I wondered at the time if I had got you to look at it and to try and unpack a little bit of what it's showing, how you would have got on. But now that we've looked at our model below, can you look at it and see some patterns? Could you have a go at explaining it? Is it beginning to make sense? So I hope that that does make sense to you, because I really have tried to push us quite far in terms of our own subject knowledge here. This is geared primarily towards geography teachers. So I've pitched this at slightly above the level that you would teach this to your sixth formers at, because I don't want you to be, as you're teaching sixth formers, butting right up to the edge of your own knowledge. I want you to have a little bit more so that you can have a little bit more command of all of this. And I have taken us on quite the journey into the world of geology. But what I want us to do now is to kind of swing back again to, okay, fair enough, that ability to see those complex diagrams and understand those from a personal point of view is great. But what does this actually look like in the classroom? Can we simplify this down in order to understand a little bit more? So I'm going to spend a little bit of time doing that before we go on our field trip, because then what I want us to do is to use that information to see how you can use this field trip and this amazing website that I'm going to show you for that field trip with your very own pupils, just like I've done. Okay, so the concept of slab pull, the concept of something sinking under its own weight. If you were to think of a comparison or an illustration or analogy for that, what might you come up with? Well, one of the things that I'll do is to take a piece of paper like this and to hold it up in front of my class. This is something that they're well used to, that the piece of paper will bend down under its own weight. And this is, in some ways, it's a useful little illustration of that process of subduction whenever the slab gets so heavy that it sinks down under its own weight. And you even get the formation of the trench there as a result of that. Or what about something like this? A chain falling off the edge of a table under its own weight, pulling the rest of the chain with it. These are everyday illustrations that you can either show gifts like this for, or literally bring something in and demonstrate it in front of the class. That's the essence of it. Something sinking under its own weight and that transferring the force up through the rest of the object, pulling it with us. And that's the essence of what we've got happening here in slab pull. And the second thing then following on from that is that as the slab pull forces are operating, they're producing this tension elsewhere. Now, what does tension do? Well, if you add tension to something, you thin it. Here's a very good illustration. You could even use an elastic band in your classroom. There's that tension force which is stretching and thinning and allowing the mantle material below to upwell. What about the notion of ridge push? If the mantle rock, when the plate slides down the edge of the ridge, it pushes and displaces the rock either side, producing the ridge push force. What about this? What about a bunch of pandas going down a slide, pushing the poor panda at the bottom down, although he seems like he is well up for it, jumping back up to do it all over again. And again, it's possible to identify these everyday illustrations, everyday examples to help our pupils to know and understand a little bit better of what we're doing here. What about the notion of a solid that can flow? The qualities of the asthenosphere, it being ductile, it's solid and it will flow. You just stand and play around with a little bit of blue tack at the front of the classroom while you're talking about that. There you go. There you have your solid but will flow piece of material in front of them. In fact, it does allow you to look at the main factor that makes the mantle ductile, and that is the heat. Blue tack that is cold is a lot more brittle. Blue tack that is warmed up, and that's why you'll rub it in your hands to make it active before you stick things up. Blue tack that is warm is much more ductile. You can stick blue tack in a piece of blue tack in the fridge and then bring it out and just see how easy it is to snap, versus when you warm it up, how it will flow. So those are everyday illustrations that you can use with your pupils to get them the essence of these things that we're trying to communicate. So what would this look like then if I was teaching this to Key Stage 3 or Key Stage 4? Well, again, we're taking out these core elements and trying to communicate them in a way that is accessible to the pupils. So the first thing that I'll say to them is convection is a process that includes and is driven by the plates. It's just something as simple as that this is not something that the plates are passive passengers with. They're the main things. These are the main characters in this story. And the second thing I'll say is that convection includes the sinking of cold, dense material, as well as the rising of hot, buoyant material. They'll be used to rising of hot material as convection. But just to introduce that idea to them that convection can include the sinking of denser, cold material as well. You can establish those, and here's a nice little simple diagram, not hugely different from the classic convection cells one. What kind of annotation might you add? The cold, old, dense plate subducts, leading to slab pull. And you can pull in your analogies there, your chain or your piece of paper, whatever it is you want to do. You could go into more detail on the nature of slab pull if you want, but there is the essence of what you need to communicate. And remember, once you have created that pulling force, it will create the tension in the middle here, and that tension will thin the plate. That will allow the upwelling of the hot mantle rock, and that will produce the ridge. Now again, you can go into as much detail as you feel that you need or want to in terms of that, but that's the essence of it. The final thing, the plates slide down off the edge of the ridge, pushing the plates apart at that point. And that's it. At least that's a good start. It's a good foundation. If you wanted a little bit more detail, you could, but there is the essence of it. And what this then allows us to do is to build this up in complexity as we move up through the key stages, adding more and more detail on. But, and this is the crucial point, at no stage do we have to embarrassingly turn around and go, oh, do you remember all that stuff that I told you before whenever you were younger in the school? It's not really right. So just ignore that now, will you? Because this is really what happens. And I suppose really that's the essence of what we're trying to do with this kind of experience, that we can't tell the whole truth about what's going on. We don't know the whole truth. Even if we did, we wouldn't have the time to tell it. But what we should tell is nothing but the truth. What we should say at the younger key stages should be able to feed naturally into what is coming in the later key stages. Use all of the analogies, use all of the examples that are going to bring this into everyday life for them. But this is the way through, because ultimately what we want to do is to take this approach in the earlier key stages to allow us to do this at A level, so that if and when they go beyond, we equip them to enter into university study of this without the university lecturers having to go, oh, all those things you were told at school, just forget them, please, because this is really what happens. Imagine if our pupils went into university and immediately they see a diagram like this, they go, oh yeah, I think I can make sense of that. That's powerful knowledge. Okay, time for us to consider and move on to think about our field trip. I've used this image before because I think it's a useful little metaphor for the challenge. Remember, whenever Wegener was looking for the evidence, all he could see basically were the continents, and it was whenever they were able to see through some of the means they developed, especially in the Second World War, when they were able to see the seafloor to get to the idea of seafloor spreading, that really brought the theory forward. But just like Wegener couldn't see the seafloor, the folks in the 60s who saw the seafloor couldn't really see what was happening in the mantle. But since then, we have developed these technologies that allow us to see better and better what's happening down there. So we're going to take the journey to the center of the earth, and we're not going to go down through a cave. We're not going to get quite to the center, and there will certainly be no dinosaurs there. But I think you're going to find this a very exciting journey anyway. And just remember this quotation from Michael Young: powerful knowledge allows those with access to it to question it and the authority in which it's based, and gain a sense of freedom and excitement that it can offer. I'm hoping that you'll get that sense of this as we go through this field trip, of this freedom and excitement, because we're going to question our model. We're going to explore the extent to which we can find evidence for it. And the evidence that allows us to do that actually comes from seismology. You'll be familiar with diagrams like this, which show us the basic structure of the earth and those different waves of the earthquake that go through that create those patterns that allow us to discern this. Now, we're actually going to take a look here at a particular example of an earthquake. I chose this earthquake because I happened to be in California whenever this earthquake happened, and really pretty cool to experience this, I have to say. This is the Ridgecrest earthquake in July 2019. And well, let's press play and watch how these earthquake waves move out. So there's the earthquake having occurred, and you can see the P and S waves moving out. Now, the waves on the surface will go out in these little regular concentric circles. There's the surface waves following. But it's as you come down here that you begin to see how these waves reflect off different surfaces and will come back up again to be measured again by the seismometer over here. And you see, even just from this one, how much complex detail you can get about the interior of the earth from the pattern of waves that come out from this earthquake. So imagine not just one seismometer recording that, but a global network of seismometers. And imagine not just one earthquake, but thousands and thousands and thousands of earthquakes over the years and the decades. And you're going to build up a pretty detailed pattern and data set of what's going on underneath the planet. And we're now round to the other side of the world, and the seismometers around there are picking this all up. And again, look at that complex interplay of all of those as they move. So we actually had seen some hints of this even before plate tectonics, the theory, had come together, and that's why we knew in the early part of the 20th century the notion of the core, mantle and crust. But what happened during the 20th century, especially the second half of the 20th century, as we started to get more and more data from our seismometers, we started to be able to get more and more detail of what lies beneath. And by the time we get to 2005, doesn't that begin to look remarkably like the model that we've been exploring. And we're now getting to the stage with this of being able to really test out the model and really see in remarkable detail what's going on down there. And the whole, the name of this data set that we're going to be looking at is Seismic tomography. And this is the paper from 1984, which talked about the first three-dimensional models that became available. Now, seismic tomography is akin to the kinds of CAT scans that you would get in hospital, or thankfully, if you need to have the doctor needs to explore something inside you, he doesn't need to cut you open in order to have a look. We can use this CAT scanner, which sends the energy waves through, and because of the reflective pattern of the waves, they're able to discern and image what's inside your body. So in the case of seismic tomography, the waves are from the earthquakes and the recording comes through the seismometers, and we're able to use that to bring together an incredible amount of detail about what's happening under the earth. But this is, in 1984, the first time that this paper came out. Now, I want you to see if you can get the sense of the excitement in this. This is an academic paper, not known typically this genre to be page-turningly exciting, but wait till you see the sense of excitement that the authors are bringing out in this. They say this: the concept of plate tectonics, introduced nearly 20 years ago, unified many fields of earth science by providing a global framework for large-scale geological processes. Seismology played an important role in the formulation of this theory by supplying maps of global seismicity, helping to delineate where the plate boundaries were, producing evidence for the deep subduction at the trenches, and determining the direction and nature of forces acting at the plate boundaries. But nearly as soon as this concept was proposed, geophysicists began efforts to explain what caused the plates to move and to derive a model that would identify the driving forces and describe the motion of material at depth. The geophysical data that have been available, the plate motions at the surface, the seismicity at subduction zones, the earth shape and gravity field heat flow, are insufficient to derive a model of mantle convection. But seismology can provide the tools for solving the mantle convection problem. For the first time, the database of this seismology material has recently become sufficient in accuracy and quantity to attempt an analysis of a truly three-dimensional structure of the mantle. And the authors say this: we believe these results signify the beginning of a revolution in earth science. For the first time, we can see deep details of the deep interior of the earth that cast new light on the origin of features observed at the surface, such as mid-ocean ridges and the enigmatic hotspots like Hawaii and Iceland, long-lived volcanic centres which are thought to be the result of plumes rising from the mantle. And we can also detect the presence of deep anomalies whose existence could not have been predicted from observations made at the surface. And this is from their paper, and I only have a black and white copy of this. The original one would have been in colour, but for the first time ever, for these images to appear to show what is happening in the mantle. The results, say the author, presented in this article are quite encouraging, particularly when one considers they are among the first of the efforts to provide full reconstruction of the three-dimensional structure of the earth. It is clear they outline the direction that a substantial part of the effort in seismology will take well into the next century. And in 2022, they're absolutely right. This is still being a major source of how we are understanding and developing our theory further. So, what does a seismic tomography scan look like? Here we go. So let's take a little bit of time to get ourselves orientated and sorted with this. First of all, the location here. This is the Tonga Trench. So what we've got here is the Pacific plate subducting down underneath the Australian plate. This is from the surface down to the mantle transition zone. This is the asthenosphere then, and this is the lower mantle down to the core mantle boundary. And this particular transect is covering a distance of around about 2,000 kilometers. The scale here is showing the speed of the seismic waves as they arrive. Okay, let's take a little bit of time to understand that. Based on our core basic seismic models, we have some reference models that tell us how fast we would expect the seismic waves to reach us if the asthenosphere and the upper mantle were more or less homogeneous in characteristics. If, however, the waves are travelling a little bit slower than average or slower than expected, they will arrive a little bit later than that model would suggest. Conversely, if they arrive earlier than expected, well, perhaps they must have been driving and arriving or travelling a little bit faster than the model would suggest. So what we're seeing here is places where the seismic waves have been slowed down by something in the mantle, places where they have been sped up by something in the mantle. Again, take a global network of seismometers and you're able to turn each of those points of data into this three-dimensional model of what's going on. And we can then infer from that that if it is arriving faster than normal, then the waves have travelled through denser, colder material, which allow waves to propagate through faster. If the waves arrive slower than expected, we're coming through less dense, hotter material, which don't allow the waves to propagate quite so fast. So red is slower because it's hotter. Blue is faster because it's colder. What that allows us then to do is to begin to see shapes and patterns in the mantle. What shapes and patterns do you see here? Now remember our setting. We have got a destructive plate margin there, a convergent margin, the Tonga Trench here. So the Pacific plate is subducting down underneath the Australian plate. Can you picture in your head what a cross-sectional profile would look like? Can you see through this seismic tomography scan the slab of the subducting plate descending into the mantle? Let's think for a moment about the quality of resolution of the seismic tomography. This is a photograph taken of Pluto. In 1994, this was the best resolution that we had. We knew there was something there. Well, we couldn't really tell anything about it. And then the Hubble telescope was pointed towards Pluto in 2001 and it was able to take this photograph. Certainly a significant improvement on what went before. And we're certainly seeing here that there are variations in the albedo on the surface of the planetoid. And that meant that whenever the New Horizons probe was sent out there that arrived in 2019, scientists knew which part of the celestial body they wanted to point at. In particular, they wanted to have a look at this area of higher albedo. And it's now these amazing photographs that came back in 2019 of that incredible detail that we've got now of the surface of Pluto. But what we see over time is this improvements in the resolution. And as you get improvements in the resolution, it answers questions. But it also prompts other questions like, what is that? And now we've got this and scientists are having a very, very detailed look at what these features are and finding Pluto to be a lot more active than they thought. But what we're seeing here is this increasing resolution over time. Now, at the moment, in terms of the resolution for seismic tomography that we would have, I would say that we're probably closer to the Hubble telescope one of Pluto than the New Horizon one, especially in towards the bottom of the mantle. We are at a stage where we can see that there is something there, but the resolution doesn't quite allow us to resolve this with the kinds of details to see it as we would like to. And it is, of course, raising as many questions as it is answering. So if we keep this in mind, that the resolution isn't absolutely perfect, but we can go in now and take a look at our field trip. This is the website that you will absolutely want to use with your pupils. The Atlas of the Underworld. What a brilliant title it is. Let's go and have a look at this. So the interface with this is very, very straightforward, very, very simple to use. You have this map of the world, which is draggable, like so. Settings, a couple of things that I just generally like to do. I like to produce a high contrast image, and I want to put on the plate boundaries here as well. So, and I click on that to get rid of it again. Let's go and have a look at a plate margin that will give us a chance to test this out. So we're just dragging these around the world. So let's come over here to South America. And if we zoom in a little bit more with the map, I'm just pressing Control to allow me to zoom in. You will know, of course, the tectonic setting here in South America. We have the Peru-Chile Trench coming here, and we've got the Nazca Plate, which is subducting in underneath the South American plate here. The subduction is happening along here, and the plate is subducting down below. Now, I wonder, can you picture again what you would expect that to look like in cross-section? Where's the subducting slab going to be? Let me just move this over a little bit more here, I think. And we can go down and have a look. There is our subducting slab. We can either look in polar view or Cartesian view. And here it is. In this case, it's subducting down to the mantle transition zone, and we're getting hints of it breaking up and coming further down here. As I say, the resolution down here isn't quite as good, but what we've just done is drawn a cross section here of the through the earth here of the mantle at this point in this location, right? And at this point, we can just go on whatever field trip we want. And we come up here. Oh my goodness, look at that. The slab is becoming an awful lot more apparent here. And at this stage, in northern part of South America, it's definitely coming down into the lower mantle. And this then begins the journey that you can go on. You can go on any part of the world that you want to and have a look at what's going on. Let's come back over here to Tonga, shall we? And we'll drag this around at this stage, and let me zoom in a little bit more. I'll drag this over here a little bit more, and let's see if we can see there is the slab descending there. It's incredible the amount of detail that we can bring in, what we can see happening at these locations whenever we see the subduction taking place. And you can go to any place in the world and you can test this out. Let's see if we come up here to Alaska, shall we? Going to keep right over there and left over there, and let's move this in closer, and the slab around here. Again, we've got this convergent or destructive plate margin coming down, and this is our ocean trench island arc. We've got the island arc of the Aleutians. So what are we expecting to see here? We're seeing the slab subducting down. Let me pull this out a little bit further here and here. Here we see the slab subducting down and getting what it looks like is getting stuck at the mantle transition zone. What you've got here in this website is the ability to go to any location you want in the world and start to draw these patterns here and draw these transects to do this field trip to see what's happening in the mantle. This isn't speculation, this isn't guesswork, this is data that you're exploring and you can explore with your pupils. Let me show you here what I do with my pupils. Having introduced that to them, I let them go into that website, and then I've given them a series of transects that I want them to go and draw and collect these transects themselves. And once they have done that, I'll get them to use what I call a digital jotter, and they will go and copy and paste these in to Google Slides, which will allow me then to go and see what they're doing. Now, I was able to demo this for them. Here's a way of showing how to go about doing it. And then this is one of my students going around his various transects, finding these slabs, marking on using Google Slides annotation where those slabs are, and showing me that he understands and can see and can read these patterns. This is our students doing this fieldwork for themselves. This is this powerful knowledge where they're questioning and testing things out. We're taking our model and taking it on a road trip. We're taking it and testing it out in the real world. And in fact, if I were to draw a transect here, as I've shown you, from this location to this location here, we can see a lot of the things that we would be expecting to see on our model. As our slabs are coming down, here's our slabs coming down, and here is a bit of a hint of a mantle plume. Now, this is one of these mysterious things that we're still trying to figure out in the mantle. This is located underneath Africa, a large, low shear velocity province. Massive, massive big feature. It seems somehow to be related to mantle plumes, but we don't really understand and know why or how that is. There are two of them. There's this one in Africa. There's one under the Pacific Ocean as well. And you get your upwelling here, which is whatever it's doing, whatever this mantle or large, low shear velocity province is doing, seems to be related to the East African Rift Valley. So it seems to be bringing volcanism along here. But what we can do as we're conducting our investigations using this website is to begin to see these patterns, to begin to test out the model that we've been showing to our pupils. So this is the kind of thing that I do with my sixth formers. Now, I could quite easily do this with lower groups as well, with proper scaffolding. Let's go and find some slabs. Let's go and find some subduction zones. And they could absolutely go and find these things. So, this is our schema again, our expanding evidence base. I would imagine that for most of us, our experience, and certainly mine before I got into all of these seismic tomography things, kind of stopped here after the seafloor evidence. It kind of stopped after we'd got to the magnetism and the age of the seafloor. We're generally well used to those. But what has happened since then has been this whole new range of data and evidence that has become available. And it's not only available to scientists, it's available to us in our classrooms. We can do this with our students. We can get them to think like scientists, right? Here's the model. Let's test it out. Let's see how we get on. Okay, so that brings us then to the last video that we're going to be doing and looking at, which is the chance to take this a little bit further. So we're going to take that model and take it even more into the real world. We're going to take it on a road test. We're going to go and explore the extent to which it works. We'll explore its benefits. We'll also explore some of its limitations and maybe get a hint of where the next piece of investigation and revelation will come in the plate tectonics theory.